and the mistakes we are here, it's not mine. This first. So anyway, first of all, I just would like to say Boris, because I know him a lot of time, and he belongs to the so-called brilliant mathematical generation in Russia. So which was include a famous name in himself, and but so you already know that he has a difficult life out of mathematics. And as you know, that it was a Warsaw Congress which say all Soviet mathematicians has a duty to go, and he was an invited speaker there. He wasn't there, minding of his talk. And so, but nevertheless, right now we know that everything was changed, and I thought about this, why he was so singular point in all these troubles. And I think that this is because his sincere love to the beauty of mathematics. Actually, he likes it and he wants to make any proof he sees the most perfect, the most exactly. And therefore, because of this life, because he really likes the beauty of mathematics, he just wrote excellent books, and he has a lot of students. And when you just write in Google and try to find his paper, which I will talk about later, and the list immediately comes his students. It's a huge list of students he has. So, but what is the good stuff? He had probably 20 years in being together in Bielefeld and having 2 months every year, just not talking about mathematics, talking about everything around. And I would like to say that it was a really great part of my life to have a conversation with research. But we don't agree with all questions. We have a different view for the many points of life. For example, the taste of cucumber outside of Russia. And he usually said that the taste is not so good as we have here, and I tried to convince him that there are several examples, and by now I also bring one new example for you to taste it in lunch, that cucumber baking. So now I would like to come back to the talk. Not necessary, because it's not necessary, just, you know, what was pushing. Okay, so the title of my talk is, as you see, it's connected to the group acting proper and crystallographic group. And this is the story. So what means the group X proper? The group X proper means that you have a locally compact space and you have a homeomorphism, subgroup of homeomorphism, and which you need that for every compact, you understand this is like this, and that for every compact set, the set which returns the compact itself has to be finite. And a subgroup called crystallographic, if you have the space of orbit is compact, or you have a compact that you can distribute around your space. So, an example is just clear. It's just one. So you can just consider the shifting by Zn, mean affine action of Zn on Rn. And the more difficult example, you can consider this locally compact space as a unitary angle matrices over real. As a group, you can consider unitary angle matrices over integers, and the action is just Gx is just multiplication. This action is also formed. But what gives? Okay, so I don't speak loud. I mean,
is it better like this?
That's okay. Anyway, so the point is that if you have a proper action and you have a point, and you look in gamma x proper, if you look on the stabilizer of this point in gamma, because of this, the set is supposed to be, because this set is supposed to be finite, this set is supposed to be finite, you have that this group is supposed to be finite as well. So stabilizer of every point is the finite group. Therefore, for example, if you look on the linear, some type of linear group, you have a linear actions, then you know that every linear group has a subgroup of finite index which has no torsion. So that means you can just escape from this situation that there is no, that every stabilizer or trivial or infinite. Okay? That's actually, so if I will do this like this, it's okay with you? You hear me? It's very good. Now, so the story, the study of crystallographic group has a long story. It started from, say, famous lecture frequent line, then Fedorov, then Schoenflies about three-dimensional action, and Brock gave it as well. So, and therefore it gave a motivation for Hilbert in his famous lecture to formulate, it was actually the Hilbert-Yates problem contains three parts. And this is the first part of this problem. He said that there is there in n-dimensional Euclidean space only a finite number of essentially different kinds of group of motion with a fundamental region. Fundamental region means that the quotient group is compact. You have a compact fundamental region. Essentially different means that up to conjugation, this group is, so you have a group, crystallographic group acting on n-dimensional space, and after conjugation there are a finite number of classes. This is what is. Now, and this is what the Hilbert-Yates problem says. In a series of papers, Bieberbach showed that this was so. So, the key result was the following. Now we can just say in a different language, but he showed that the following, that if you have a crystallographic group, that it contains n independent translation, linear independent translation. In our language it says the following, if you take if you have a group acting isometrically on n-dimensional space, then this group contains a subgroup of finite index which consists just of parallel translation, or it contains a subgroup of finite index which is abelian. Okay? So, and I know that there are a lot of, so it's, but this is what and he, based on this result, Bieberbach showed that there is essentially a finite set of group acting isometrically on n-dimensional space. Okay. So, the natural way to generalize this situation is just to consider a border class of motion. For example, you can consider the affine group. What does it mean affine group? It's actually the combination of linear action plus shifting. And this group acts on affine space, and it would be actually interesting to ask if the straight generalization of Bieberbach theorem can be proved here. Namely, if you have a crystallographic group acting on affine space, then the question is if its group is virtually solvable, virtually abelian, like before. So the example, this example shows that this group acts here proper. The space of orbit is compact, but this group, of course, is not virtually abelian. Therefore, a straight generalization doesn't work. Therefore, Auslander conjectured the following famous question, and the question is the following. So, if you consider the crystallographic affine group, is it correct that this group contains a solvable subgroup of finite index? Or namely, it's virtually solvable. Actually, it was stated not as a conjecture, it was stated as a theorem. And it was immediately clear that the theorem contains a gap, And the problem still open and became a central probabilist in this theory. An additional interest to this problem is the following. So if you consider a fine, complete, locally flat manifold, which doesn't matter what it is, you can consider the following. You have a fine, complete, locally flat manifold, and the universal covering of this manifold is Rn. So it's covered by this is universal covering of this manifold. And the fundamental group X proper, and therefore your manifold is this portion. So of course this group has not had torsion, but we know that this group is linear, so it's not a problem. And so the question is, what group might be the fundamental group of, the question belongs to Müller, what group might be the fundamental group of a fine, locally flat, complete manifold? Müller proved, this is also his question, and actually, let me just, okay, so what Müller proved? He showed that every virtually polycyclic group, or say, polycyclic group means you can consider the following. We take a subgroup of triangle matrices, and there is for this group, you have a chain of normal subgroup with a cyclic quotient. This is polycyclic group. And he showed that every polycyclic group can be realized as a fundamental group, without torsion of course, can be realized as a fundamental group of complete, affine, locally flat group. But the reasonable question is, you see the polycyclic group, if you have a polycyclic group, this group has is a series of normal subgroups. And the quotient is cyclic. So what you would like to say, to take a one parameter subgroup and to cover it as cyclic. So the normal and reasonable question, which is stated at the next question, is the following. If you have a torsion-free, virtually polycyclic group of rank K, rank K means how many numbers, how many cyclic factors you have. So, and the question was if you can find a K-dimensional compact, complete affine manifold with this group as a fundamental group. Okay? So this is reasonable. For example, Z10 you can put in Rn. So, but if the algebraic structure became more complicated, what you can do? Fritz Grunewald proved that this is the case. And the next day he showed that it's not true. So a lot of mysteries are going with this Ausländer project. So again, Fritz Grunewald gave a talk where he showed that this is true. The answer on this question is yes. And then the next day he found out that counterexample, and the answer is no. Moreover, if Benoit showed that this is not true, even you restrict your group up to the nilpotent group. So it's not true that every nilpotent finitely generated group can be a fundamental group of a compact, complete, locally flat affine. So the next question he said, and I will explain a little bit later what was the reason of this question. He said the following. Does there exist a complete locally flat manifold such that the fundamental group contains a free subgroup? Okay? So, and he made a comment, and let me just show the picture.
Free group, but even one generator.
No, absolutely free, which means non-abelian. Non-abelian, of course not. Because, no, it's, Müller has a question reason. So, and actually what I would like, I will cover a little bit here to show you what he says. So, this is the picture he had in mind. So, if you consider what he said, if you consider an affine group, which is a linear transformation in a form of signature 2-1 invariant, you have the following structure. This group actually has the following. You have an invariant line, and you have two subspaces. One is repeating, one is contracting. And what you think is the following. You have two these elements, one like this and the other like this. And what he wanted, so it was absolutely clear that you can find two such elements and they will generate a free subgroup. It's up to this. So, but you have to add a linear transformation or parallel translation. And he said, what is difficult, it's difficult to control what happens with parallel translation for the product. How they will go together. So what you can say, if you have one parallel translation, other parallel translation, you produce a word, how this length is going far. And he mentioned that this is, to control this is difficult. It's actually not just difficult, it's actually interesting to do this. Now let us make a comment why he actually made this, stated this question. In this time, Tietz already proved his famous Tietz alternative. He says the following. If you consider the finitely generated linear group over, doesn't matter what characteristic is, then you have alternative. Or this group contains a free subgroup, absolutely free, namely non-commutative free subgroup, or this group is virtually solved. Therefore, Milner thought the following. If you have a finitely generated linear group, which is supposed to be the fundamental group of your locally flat affine manifold, you have alternative. Or this group is virtually solvable, and therefore it's, of course, virtually polycyclic, or it has to contain a free subgroup. Therefore, the question, is it true that this alternative happened for the fundamental group of affine manifold? Or they contain the free subgroup, or they are virtually solvable. So to explain how it works, let us explain the following situation, so how it works. So this is the definition, the standard definition which has come to the, so you have a affine group. This group is so-called semi-direct product. Namely, you have a normal subgroup which contains just translation, and you have a linear transformation. And this group acts on points, not on vectors, on points. So, you have a natural projection of this group onto this linear group, and this part of your element G, so-called linear part of transformation. And you have subgroup or subset, this is so-called the linear part, not of X, but for G. This letter is not correct, it's supposed to be G. So all linear parts of your set is linear parts of your. Now, let me just say the following. So we know that the affine group has a linear representation. You can just increase the dimension. So the representation is well. So therefore, you can consider for every affine group, you can consider the Zariski closure. And it's not a big problem because of this stabilizer property. Because of this stabilizer property, follows that if your group acts proper, then every element in the connected component of the Zariski closure has 1 as an eigenvalue. Okay? Otherwise, you have a fixed point. If you don't have an eigenvalue 1, you will have a fixed point. Because solution of some. Okay. Now, therefore, the structure of your affine transformation is just a little bit difficult to I can try it here. So the structure of your affine transformation looks like this. You have a line, invariant line for every affine transformation. This is a parallel line along your eigenvector with eigenvalue 1. Now, let me just explain. So let us look on the Bieberbach theorem from this point of view, from the point of view of the Tietz theorem. So I would like to show you one proof, and I do remember that I saw someone, with your paper, when you also proved Bieber-Bach theorem. This is correct, yes? You have a paper with the proof of Bieber-Bach theorem. But I didn't find it, so I have no reference. And I decided, okay, let's me also to give another proof of the Bieber-Bach theorem. So what is the proof that we can prove, how we can prove the Bieber-Bach theorem using this teeth result? Assuming that we have a group acting, now we are in a Euclidean situation, so we have two elements which are, actually, our elements act isometrically on our space. We are talking about the Euclidean case. We are talking about Bieber-Bach theorem, and we would like to show that if we have a group acting proper, if we have a crystallographic group, then this group contains a abelian group of finite index. As a first step, we would like to show that this group is virtually solvable as a first step, because the further steps are very clear how you can go from this. So what you have two isometric, you have two elements, G1 and G2. And if you assume that your group doesn't contain a solvable subgroup of a finite index, then you can contain a free group. So you can assume that you have two elements, G1 and G2, so that the group generated by G1 and G2 is free. And now you would like to have a two situation. You can just measure the word length, so we have a board in a free group. You can measure the word length on one side, and so on the other side we have to measure how far you move the point. And it's clear that you move the point, if you have this point, that the norm is going linearly, because how you do? You can take the point, you move by this one, and then you move by this one, by this. Both are isometry, so they keep the length of one, so they just add it. So the behavior of your norm is linear. The number of words you can produce is exponential. If your length is going linearly, then you are in a ball which volume of the ball going polynomial. But you have exponentially many words inside, so you can make it as close as you want. So, and therefore, for every epsilon, you can find two words which are close. But if you apply inverse, you will not change the distance. But it means that you move this point very short. You're still in the same point. And therefore, you come to contradiction. This group doesn't act proper. Therefore, this group is virtually solvable. And the next step, we immediately have that this group is virtually solvable. So this is another group. Okay. Now, but what we can do with the Newton conjecture? How we can just set there? So let's just first start with Margulis' definition. So Margulis answered on this question positively in 1987. So, and his approach was absolutely surprising. Because actually when we discussed it about how to prove this, we thought that the answer is supposed to be no. But then he found out that the answer might be yes. And what plays an important role? So let us do the following simple algebraic exercise. So consider the non-degenerative quadratic form of three variables, x1 squared, x2 squared, minus x3 squared. Okay? Now, then you can find the basis in your three-dimensional space according to this orthogonal basis according to this quadratic form. But it needs to be this vector is 1, and this is minus 1. Okay? Now, if you take gamma, let's gamma be the subgroup of a affine transformation, so that the linear part of gamma is a semi-simple matrices, which means that it's diagonizable. Diagonizable means that this linear transformation has three vectors. One with eigenvalue lambda, the other with eigenvalue lambda inverse, and the last one with eigenvalue 1. Okay? This is just so then we will make the orientation, we have this, we oriented this basis v plus v minus v0 as the standard basis we choose in the beginning. Okay? So we have two orientations, so we oriented them as we have. And we define the sign of the transformation in the following simple way. Take a point, move the point, multiply by d0. Okay? And multiply by d0. This is definition. I will explain the geometry, dynamic, which is stayed behind these definitions, but this is a different story. This is what I would like to say. This is the definition of the sign. Now, let us look what will be the sign of the inverse transformation. What does it mean? Because the idea is the following. If the sign determine dynamics, means that if you're going in this direction, the sign will change, you hope that you're going in the back direction. How you can change the sign? Usually you can take it by taking inverse. Look what's happened here. Now, if you take inverse, then these vectors, v plus and v minus, will switch. Okay? Therefore, the v0 is supposed to have a minus if you need to keep the same orientation. So the v0 for gamma inverse will be minus v0. Take this point, apply gamma inverse, you have this point. Okay? And therefore, this means that this is exactly the sign of the sign of gamma inverse. The sign of gamma inverse is here. And this is the same as the sign of gamma, because double minus is giving plus. So the sign will not change. And what is the main point? The main point is the following. Look at this picture. So if you have gamma 1, and if you have gamma 2, the sign actually means the following. This is, say, the vector is extending vector. This is lambda more than 1, and this is lambda less than 1. Lambda inverse. So you are going along the invariant line for gamma 1, you are going in this direction. You are going along this line in some direction. The question is what's happening. You started from here, and you can move to any point in the intersection. Then, you pick up this point and move by gamma 2. The question is where you are going. You are going in the same direction, you are going back. If you're going to the back direction, what's happened? You have two compacts, you can move from one compact to another by different words. Okay? But it means that if the picture is like this, your group doesn't act proper. If the picture is like this, so they induce a different direction along this line. But this is exactly what happened if these two elements has a different sign. This is the text of the picture. If alpha gamma 1 multiplied by alpha gamma 2 has a different sign. Namely, the simple remarks show that if you have two elements with a different sign, then this group doesn't act properly discontinuously. And then you have to say, what's happened if your elements have a two, the sign of these elements are the same. The main advantage is that if you take an inverse, they will still have the same sign. Okay? And therefore, based on this idea, Margulis proved that if you take two elements with a positive sign, then you can take a big degree of these elements. You have two things. What? You have group which is free, because element gamma 1 and gamma 2 in the big powers generate a free subgroup. This is the first. The second, because they have the same sign, this group acts proper. Therefore, you have a free group which acts proper on affine space in dimension 3. So, later, just developing this idea, together with Herbert, with Albers, Margulis, and myself, we proved the following theorem, that if you have group which leave the form of signature n plus 1 n, the linear part, it's invariant. So, n, it depends on m, what you have. It definitely depends on this m. If this m is even, and your linear part is the risky dense, this group doesn't act properly discontinuously. But in the case of this odd, if M is odd, there is a free group such that the linear part is the risky dense, and group acts properly. So we have this case in all dimensions. Then we continue to work on this, and we show what's the situation as we call in the geometrical setup. So if your group, not just a affine group, but together you have some geometry, namely this group gives some form invariant. A form is of signature PQ. So, and what we prove that if you have this group, if gamma is a affine group, so that the linear part is the risky dense here, and the difference between P and Q is more than 1, then gamma doesn't explode. So let me explain the motivation why we just consider this, why we look on the linear part. So if you wanted to prove that your group is virtually solvable, you have to prove that your linear part is virtually solvable because you X by a billion group, you factor it by a billion group. Therefore, the whole algebra is in the linear part. So as smaller you can do, you can squeeze your linear part, as better chance you have to prove that this group is solvable. Therefore, for example, it cannot be the risky dense in a big group. So we have a subgroup. Actually, this result helps us to prove the Auslander conjecture in case when T is 2, but I will talk about this later. Okay, now let's come to the Auslander conjecture. The development here was started by Goldman and Fried paper. They proved the Auslander conjecture for dimension 3 in 87, and then for a long time it was no progress. It was in many papers starting to prove the Auslander conjecture in several situations. The name is there, and finally, which was independently done by Tomanov and myself, so that if you have the situation when the linear part of your affine group is in a semi-simple group such that every simple component has at least a rank is not more than 1, then your group is virtually solved. So when I started, I would like to be more or less along the table, because the next step will be lunch, and it's not going to be people. So when
it was 12:05?
I started 12:05.
So you
No, I can calculate. It's okay. So I would like to just briefly to explain what result we had, because I would like actually to say about the problem stated. There are a lot of problems, it's very deeply interesting. So first of all, we proved the Auslander conjecture in the case where a group is acting with the affine space and leaving the form of signature P2 invariant. Idea is completely different from the ideas which are here. Based on the dynamical ideas, we developed the definition of the sign of affine transformation. We make it a little bit different, not just a sign. We just constructed and show that there is a cone of direction. If this cone contains 0, then group doesn't act properly discontinuously, and all proof is going to show or to calculate what is the cone of this group generated by this other. And recently we proved the Auslander conjecture in full without any restriction up to dimension 7, not included. And I explain the reason and formulate the problem right now. So, bottom line, up to now, the Auslander conjecture is proved for dimension of a affine space less or equal 6. No. Okay. Now let me make, just formulate some language which lets me to formulate problem a little bit. So, look at the affine group. You know that this group is a semi-direct product. It contains a group, normal subgroup, consisting just of parallel translations. And then you can consider the intersection. The meaning of this group has two there are two meanings of the group. On one side, this is a normal subgroup of gamma. On the other side, this is a subset in your affine space. Therefore, you can take the span of by this affine subspace spanned by this point, or by this point. And this affine space, of course, is invariant under the gamma. So you can induce a new action on the factor space, affine space, modulo this affine invariant subspace. And the main advantage is the following. So your group gamma X proper or is crystallographic if this factor group X proper or is crystallographic. But the intersection of this group, therefore we can assume that the intersection, this intersection is trivial. That's what we can assume. Therefore you have this map, linear map, linear. If you map your elements to the linear transformation, you can have a map back. So your linear part, actually this group gamma, is deformation of some linear subgroup. Okay? So therefore you can formulate the following. Take the gamma 0, take this subgroup gamma 0 as a linear subgroup. And you would like to deform it to have a affine group. And you can ask if this group X proper or this group is a crystallographic. Therefore, according to this, we will say that deformation is proper if you have, as a result, you have a group, affine group acting proper. So again, you have a discrete linear group, you deform it to the affine group, and you'll ask if this group X proper or this group became a crystallographic. So everything now clearly depends on the linear part. And in his talk in the previous international program, Goldman stated the following question. He actually asked what linear group might be, discrete linear group, might be the linear part of a affine group acting proper. So he said it is actually a question. So, and let me now come to the important part of the talk, properties. So, as we know, what is proved by Mercury is that you can construct two elements with the positive sign, take a big power, and you have a free group acting properly. The question is the following. Assume that you have a linear group, you would like to ask, and assume that there is a deformation such that every element of gamma has a positive side. All elements in your gamma has a positive side. Question. Does this group act properly? So you cannot take a big power, but you would like to show that the group is proper because of translation. So, and the answer is given by the big paper in the Adams and Goldman, Margulis, and Lebohé prove that answer is essentially yes. There is some. Okay, but essentially the answer is yes. So what? They introduce a new.
Essentially, yes.
Yes, because they introduce a new changing a little bit sign. So, and on the other case, there is a very interesting connection between a surface group and group acting properties continuously. Namely, in the very beginning, it was stated by Goldman probably. If you look on the gamma 0, the fundamental group of a compact surface, the question, can you deform this group in a way that the group will act proper on a affine space? This way. Can you make these deformations such as it will be proper deformation? The answer is no. First, it was proved by Mess with a hue in a very big paper, and then, because of brilliant idea belongs to Goldman, he actually understands that the deformation of this group, the deformation of these groups here, and the deformation of this group, discrete subgroup of L2, namely the Teichmüller space, they have a very interesting connection. Namely, sine is the tangent vector to the curve in the Teichmüller space. Okay, this is not a simple connection, but I would like to express that there are a very deep connection between Teichmüller space, between the deformation of in a SL2 and deformation in SL2R, SL2-1 as an affine group. Okay, and so this was realized in the Goldman and Margulis paper, and they showed that no fundamental group or compact surface group cannot be deformed such that they explode. So the next question was stated by Goldman immediately, because we know that there is a free group acting proper, we know that there is a solvable group acting proper. The question is there non-free, non-solvable group which acts proper. So recently, Danziger, Burrito, and Castle gave a positive answer. So the point is they did the following. So it's also the place to say. They consider the group of discrete, they consider the discrete subgroup of a group of SON1, hyperbolic group. What is a group? The group generated by reflection. What is the angle? The angle is the right angle. So they consider the group generated by reflection as right angles. And they deform this, they make a deformation of this group in a parallel. They deform it here in SO21 and glue this deformation with the deformation in a affine group and show that the group still act proper. But the dimension what they quoted was very big. Giraud tried to convince me that it's not too big, but I think it's too big. Because we have the following equation. So we stated with Margulis the following equation. If there exists a non-virtually free, non-solvable subgroup of affine group acting on 8-dimensional space, just 8. So why this was stated so? Why we just look at the 8? Because in some paper we together with Margulis proved that there is a subgroup which is a free product of Z2, namely abelian group Z2, and free, absolutely free group. But we showed that this group exists as SL4Z. Then I showed that it can be deformed to the discrete subgroup in SL3R. So again, we have a discrete subgroup in SL3R, which is a free product of abelian group of rank 2 and absolutely free group F2. And now you can consider the joint representation of this group, and you will have an 8-dimensional representation which sits in the SO353, because the signature of Killing form is 5'3". And you have invariant line. So as Milner suggested, you have this group. This group is just containing hyperbolic elements, namely this picture is correct for them, and two subspaces. And you would like to add just linear transformation, parallel translation, and follow what's happened, how far you can move, or if this group still acts proper. Just add to this invariant line. So, and this what I think it's probably can be done, and this is, I guess, quite interesting problem. So the next question is, of course, if you decrease the dimension, can you prove that if a group acts proper, and I believe that the answer is yes, the answer is no, then it does contains Z2 as a subgroup. So because of this, our result on our standard conjecture up to 7, it's look like it's, you can show that there is no Z2 inside fundamental group, they mean there is no torus, two-dimensional torus in your affine space, in factor. So, and that's it. Thank you.